When there is lack or deficit of charges on a material, those were known as positively charged. So he named the charges as positive and negative. So he found out that unlike charges attract each other and like charges repel from each other. Electroscope is a material which can detect the presence of electric charge. When I bring a positively charged material near to this conductor, what will happen? Hey all, I'm HK from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, Mysuru. In this chapter, we are going to deal with electric charges and the fields that surround them. So electricity is actually everywhere around us. The phones we use, the communication devices we use, the tablets, the laptops, the systems, everything has electricity surrounding them. Even if you look up, we can see lightning and that is electricity. Even if we look inside our cells, we have electricity functioning, coursing through our veins actually. We need electricity for our muscles to communicate to each other. We need electricity to think properly, clearly. And even with electricity, some people have trouble thinking clearly. And so in this chapter, we'll be discussing about electric fields and the importance of electric charges, the basic properties of them, how they interact with the surroundings, what are their special nature, and everything will be discussed in this chapter. This is amber. This is a naturally occurring substance in nature. Just like you find glass or like rubber or like any other materials, these were also very common on Earth. And then in the early 16th century, it was found that when amber was placed near certain dry leaves in winters and all that, the amber seemed to attract dry leaves. And this was first observed in the 16th century. And later in the 16th century, when women went to parties wearing heavy silk clothes and like luxurious fur clothing and all that, they would just rub these rocks and place it near frogs, and the frogs would have a jump scare. And they did not know why it happened. They just did it for fun. And it was later in the 18th century that a physicist named Benjamin Franklin who found out that why this was actually happening. And then it was Benjamin Franklin who found out that when certain substances were rubbed against certain other substances such as cloth, silk, fur or anything, they seem to have an attractive or repulsive property. Why was this happening, and is this similar for every material? So this thought led to more experiments on this matter, and later he found out that certain substances, when rubbed against certain other substances, were sticking onto them or were repelling them. So we also face these things in our daily lives. That is when in winter seasons and all, when we comb our hair, when it is very dry, and when we keep it near a loosely hanged tissue or like a bits of pieces of paper, it seems to be stuck onto each other. And similarly, it's the case of balloons. We can see that kids who rub their heads against balloons, and when the balloon is kept near paper towels or like other things, they seem to attract each other. And in very dry seasons, especially in Mysuru and Bengaluru and all that, when you just pass nearby each other or when you touch a person, you get an electric shock. And all these was due to the same reason. Why is this happening was discussed and found out by Benjamin Franklin in the 18th century. So what he found out was that when certain materials were rubbed against certain other materials, there was an excess of charge or there was a deficit of charge. So how exactly he found out that was when he charged a glass rod. Let's say he took a glass rod and rubbed it against some silk or cat fur or something. When he brought it near a balloon, then the balloon seemed to be attracted towards the glass rod. Then he charged it again, he rubbed it again with cat fur instead of silk. And then what was observed that the balloon seemed to be moving away from the glass rod. So based on these conclusions, he concluded that there were two types of charges. One was positive and one was negative. He named those charges as positive and negative. And he concluded that when there is lack or deficit of charges on a material, those were known as positively charged. So he named the charges as positive and negative. those two charges, and innately an object will be neutral when the number of charge carriers are equal in them. When a material has equal number of positive and negative charges, that material will remain electrically neutral, or it won't have any charge. It won't attract or repel any object. But when you create an excess or deficit of charges, these materials will definitely attract or repel certain objects. And why this happens is what we are going to study in this class. So basically what Benjamin Franklin found out was that when you rub a glass rod with silk or fur or something, it used to develop some charges. Let's say this glass rod had positive charges in them. So when a material was brought near that positive charge, it was attracted only because that material developed a negative charged region that was attracted towards the positively charged region of the glass rod. So because of the difference in charges, these were attracted to each other. So it was found out that materials had charges in them. Materials had two types of charges, which was positive and negative. And these charges seem to attract each other. The positive and negative charges, which are opposite in nature, attracts to each other. And while the same kinds of charges, let's say two positive charges are brought near to each other, then they seem to have a repulsive attitude towards each other. You cannot bring them close to each other. It's like those two friends who would never bond to each other. When you try to bring them close to each other, they just want to move away. That is how the similar kinds of charges behave. When two positive charges are brought near to each other, they just seem to want to move away. And when negative charges are brought near to each other, they also seem to want to move away from each other. So what Benjamin Franklin actually observed was that when unlike charges were brought near to each other, they seem to have an attractive property. And when like charges were brought near to each other, they seem to have a repulsive property. How this was actually observed? Through experiments and through the daily life observations. When you comb your hair on a dry day and you place paper bits nearby it, it was found out that they had an attractive property. So this had only one conclusion. That is, the comb was in a charged state which was different than that of the paper bits. That they were unlike charges, and that is the reason why this sticky nature happened. So the basic baseline is that unlike charges attract each other. So based on all these inferences and conclusions, Benjamin Franklin actually arrived at certain inferences. And those were, charges were differentiated as positively charged substances and negatively charged substances. And charges had similar properties. That is, positive charges always attract negative charges and negative charges always attract positive charges. So he found out that unlike charges attract each other and like charges repel from each other. And it was Benjamin Franklin that came up with the concept of polarity. You have heard about North Pole and South Pole, the poles of a magnet, which just is there to differentiate things. So basically, the property which differentiates two kinds of charges is known as the polarity of that charge. So there are two kinds of charges, which is positive and negative. So that is the polarity of that charge. And polarity just means that the property which differentiates them from each other. So one will be positive and one will be negative. That is the polarity of charges. And the important thing is that positive charges are attracted by negative charges, and like charges such as positive and positive or negative and negative repel from each other. Those are two friends that never hang out together. And it was also found that certain materials had certain properties. So we are going to understand why certain materials attract certain materials, why other materials slightly feel shy not to attract certain materials. We are going to look at all this from the standpoint of view of charges, that is positive and negative charges. Does these charges has anything to do with the way materials attract each other or behave in certain ways? So it was later found out that there were certain materials which had free charges that could roam around the surface of that materials, and certain materials where the charges seem to be crowded to certain areas. And those materials were known as conductors and insulators. Or simply we can say that materials which allow charges to move freely about the surface is known as conductors, where materials which do not allow charges to freely roam about the surface is known as insulators. Or you can simply say that materials which allow electric current to freely pass through them are known as conductors, and materials which do not allow electric current to pass through them are known as insulators. So there are materials which has free charges roaming around their surface, and there are materials which do not have free charges roaming around their surface. So materials which has free charges, which is free to move about on the surface, is known as conductors because they can conduct electric current very easily. But certain other materials, charges will be concentrated in specific regions and they won't be distributed evenly. So these materials are known as insulators, and those materials which can conduct electric current very easily is known as conductors. So there is a question, how do you know when materials are charged or not charged? How did Benjamin Franklin know when materials were charged or not charged? So for that, he used an equipment known as an electroscope. Electroscope is a material which can detect the presence of electric charge. Electroscope is an apparatus which can detect electric charges. So what it will be is that it will have a knob, like a round knob, and it will have two leaves which is made of metal. So it can conduct electric charges very easily. So when you bring, let's say, a charged particle, a charged glass rod, so what will actually happen is that the electric charges, when comes into contact with this metal knob, the charges from this surface will travel through here to all this leaf. So when the charges travel from the knob to the metal leaves, you can see that the charges are similar. So when the positive and positive charges come close to each other, automatically there is a repulsion among them. They don't like to talk to each other. So what will they do? They'll try to run away from each other. Depending on the strength of argument between them, that is the strength of the charges being distributed amongst them, the spread of this leaf will be that much. If there is only a small argument, if there is only a small amount of charge given, the spread will be low. And if the argument is very big, like you have kept a secret from your friend or something, then the spread will be really high. So depending on the strength or intensity of the charges distributed, the spread of these leaves will be based on that. That is, if less intense charges are given to the leaf, the spread will be that much. And if more amount is given, the spread will be more. And how do you know when certain materials are positive or negative? There is actually no way of knowing if it's positive or negative. You can know that if the charges are like charges or unlike charges. A negatively charged rod near this and remove away the positively charged rod, what will happen is that these negative electrons will try to pair with each of these positive charge and the spread will decrease. So this will be like a friend coming in between those two people and saying that things will be fine, it's not much of an issue. So what will happen is that the charges will get neutralized. So for every positive charges, there will be negative charges. So depending on the amount of charges distributed, the electroscope will reduce its spread. So if the friend is really strong as the argument given, then it will be neutral. All the charges will be neutralized. If the friend is only there to comfort you and say that for now don't make it a scene or something, then the argument will be less, but it won't vanish. So just like that, when there is enough positive charges or like charges, the electroscope will spread or the charges will repel each other. And when the opposite charges are given to that electroscope, the charges will come close to each other. That is, much of the charges will get, let's say, if this was the initial spread and then the negative or the opposite charge was introduced, then the spread will lessen to this region. That is because opposite charges cancel each other out. So another thing that was observed with charges is that when you have a charged body, let's say I magically charge this metal sphere with negative charges. So now this metal sphere has lots of negative charges, and I don't want this negative charges to be there. Who wants to be surrounded by negative energy, right? So I want to get rid of this negative energy. So what can I do? Not negative energy, this is negative charges. So how can I get rid of this negative charges? So one way of doing it is that if I stand here, if HK stands here and touches this knob right here, you can see that I am standing on the ground. That is earth. So when I'm standing plant footed on the ground and when I'm touching this knob, a contact is established between this metal sphere which is charged. So the ground is considered as a huge electron bank, which means that the ground has enough charges to neutralize anything. So basically what happens is that all the charges that are excessive or deficit in this metal sphere will get traveled through the circuit, that is me, to the ground. And what will happen is that all these charges will get neutralized and there won't be any excess charge on that metal sphere. So why does this happen? Why does charges go here and there? So why this happens is that nobody likes tension, right? Nobody wants stress in their life. Nobody wants to have any tension or much pressure. So similarly, charges also don't want to be in a state of stress or unevenness. So what they would always want is that they would want to combine with each other and neutralize their effect. So that is why negative charges will always seek positive charges and positive charges will always seek negative charges so that the balance is restored, because they always prefer an energy state which is low. To compare, if you're sitting in your home and if you have to do some work, you don't generally want to do that work. You just want to sit there, relax and watch TV. Just like that, when they are alone, they are having a higher energy. So to avoid that, they will always seek positive charges so that the balance is restored. Nature has a way of balancing everything around us. So nature has a way of balancing everything around us. That is why the charges are eager to go to the ground and meet the positive charges and get cancels each other. So that process where excessive charges are directed down to earth is known as grounding or earthing, because we are directing the excessive charges to the ground. So this is known as grounding. That is the process of induction. We can actually, without even touching the material, we can make a material positively or negatively charged. So how we are going to do that is through induction. So what exactly happens is that when you bring a positively or negatively charged rod near to a metal sphere, it will generate a charged region. That is, when you have a metal sphere, even if it is completely neutral, this is a conducting metal sphere because charges can freely move about the material. Let's say a positively charged material. When I bring a positively charged material near to this conductor, what will happen? Initially, all the charges will be distributed like this. Randomly distributed. So what will happen is that if I am bringing a positively charged rod near the metal sphere, the like charges will repel each other and the unlike charges will attract each other. So what will happen is that I'm not having physical contact with the metal sphere, I'm just bringing it close to it. So what will happen is that all the negative charges, like a princess who wants to see the knight in shining armor, will go running out the window and waiting for her charming prince to reach there. And all the positive charges, like a scared little bunny, will run away from it. So there will actually be a region which is negatively charged and a region which is actually positively charged. So that is what is happening here. So a metal sphere is used because charges can freely move about the material. So when this glass rod which is negatively charged is brought near, it's an ebonite rod, it's fine. So when this rod is brought near a metal sphere, a region of positive charges and a region of negative charges are developed because of the influence of this negatively charged rod. Now what we are going to do is, we are going to take a wire and connect it to the ground, or we are just simply grounding it, or you can simply use another metal sphere and keeping it in contact while keeping this ebonite rod near to that. So what we are going to do is, we are going to connect a wire from the metal sphere to the ground. This is the symbol for grounding. If you don't know that, this is the symbol for used for grounding. So we are going to connect that to the ground, and what will happen when we connect it to the ground? All the excessive charges present here will run off to the ground being happy, because they want to be free and they want to have a minimum state of energy. So they want to find the positive charges, combine with them and neutralize each other. So all the negative charges will run down to the ground. And what happens when all the negative charges run off? You are left with only the positive charges. So after that, keeping it for some time, we'll just remove that wire and we'll remove the glass rod. And then what we are left with is a sphere which is positively charged. When we remove this glass rod away from each other, all the concentrated charges will redistribute itself in the metal sphere, so that we'll have a positively charged metal sphere. So this process is known as charging by induction. So what basically happens is that when a charged glass rod, ebonite rod, or whatever it is, a charged rod is brought near a conducting material, there it will generate charged regions, that one will be positively charged and one will be negatively charged. If you are bringing a negative charged rod near the metal sphere, the region near to the glass rod will be positively charged and the region facing away from it will be negatively charged. And depending on what type of charge you want, you can use it accordingly. If you want negative charges, you bring a positive rod. If you want positive charges on a sphere, you bring a negative rod. It's fine. And then you connect it to the ground, or you ground it, and the excessive charges will be removed. And when you remove the glass rod away from that, you will have a charged metal sphere. You must note that there is no contact between the materials. You're just bringing it close to each other. You're not touching it. There is a gap in between these two, and this is known as induction, charging a material without actual contact. So we have seen that charges has many properties. Unlike charges attract each other, like charges repel from each other, and charges want to have a state of minimum energy. So what are the other properties about charges? What are the things we need to know about them? So this will be discussed right now. That is the basic properties of charges: additivity of charges, conservation of charges, and quantization of charges. So if you have a system of charges, randomly, let's say there are many charges in a sphere. Charges are denoted by the letter Q, either capital Q or small q, depending on how you want to choose it. It's completely fine. Generally, charges are represented by the letter Q. So if you have a material which is charged, then the total number of charges, because you can see that there will be positive, positive, positive. There will be many number of positive charges on a single material, because there won't be just one positive charge in a material. There will be many number of positive charges. So how do you know how much charges are in the material? How can you add it? Can you even add it? So it turns out that you can actually add charges in a material. Depending on how many charges there are in a material, you can add it as it were numbers. If you have 5 apples in a basket and you add 3 more apples, then you will have 8 apples in total. Like that, you can add charges just like that. So imagine you have a basket and somebody dropped 10 apples in them. And let's say one of your friends came and had 2 apples. So how many apples were there in total? So initially there was 0 apples. Then somebody dropped 10 apples in them. So now you have 10 apples in the bag, but your friend ate 2. So 10 minus 2, you have 8 apples. That is exactly the way how we are going to add charges. So you can add charges like they were scalars. Charges are additive, which means that the total charge on a system is equal to the algebraic sum of individual charges on the system. So let's say that you have a metal sphere having 3 charges. So there are Q1, Q2 and Q3 charges. So what is the total number of charges? It's simply, let's say capital Q is the total number of charges. Then it is simply Q1 plus Q2 plus Q3. So this will be the total number of charges. That is just how we can add charges. So that is, if a system contains n number of charges, 1, 2, 3, 4, etc. up to n number of charges, then the total number of charges on that system will be equal to Q1 plus Q2 plus etc. And if those are positive charges, then plus 1 plus 2 plus 3 plus 4. And if there are negative charges in that system, you just have to subtract that. That is, if you have plus 1, plus 2, minus 3, plus 4 and minus 5 charges in a system, it just means that the total number of charges in that system will be the algebraic sum of all those. You add 1 plus 2, which is 3, minus 3, plus 4, minus 5, which up to this is 0, and plus 4 minus 5 is simply minus 1. So the total charge of that system is minus 1, which means that that system or material is negatively charged. So that is the first property, charges are additive. You can just add them up like numbers. The second property is that charges are conserved. You cannot magically create or destroy any charges, which just means that if you have a system of charges, you considered again a metal sphere. So this metal sphere is our system, and there are n number of charges in this system. If an isolated system, which means that nobody is interrupting that system, no energy is given to that system, no energy is taken away from that system, you're not establishing any contact which creates variables in that system, then that system will remain conserved in the case of charges. Which means that when one material is rubbed against another material, and material can gain or lose charges, but the total number of charges will always remain constant. You cannot magically create or destroy charges. So that is what is meant by charge is conserved. So that is the second property. The first property is charges are additive. Second property is that charges are conserved. Charges are quantized, which basically means that if you have n number of charges in a system, let's say you have 8 charges in a system, and let's say that Q is the charge of one single piece. So we can say that there are 8 number of charges, which means that 8 into Q, which is 8 Q charges are present in this system. If these were electrons, which is denoted by the letter E, there are 8 into E, which is 8 E electrons present in that system. So that is the meaning of charges are quantized. That is, charges will be integral multiples of a base unit. So the charge of an electron is given here, which is 1.602 into 10 to the power minus 19 coulombs. So coulomb is the unit. So one more thing to remember in physics is that you should never ever forget about SI units. Anything you write should have an SI unit right by that, because we are very adamant about measuring things and having units by them. So the 3 properties are that charges are additive, you can add them up as numbers, and charges are conserved. You cannot magically create or destroy charges in an isolated system. And finally, charges are quantized. That is, a system contains n number of charges. Those will be an integral multiple of a base charge. So these are the basic properties of charge. And finally, since we understood all the basic properties about charges and what charges exactly are, let's see what happens when charges come close to each other. How they exert their forces or how they behave to each other. All this was studied by a French scientist who's known as Coulomb. Out of respect to him, we have named this SI unit as Coulomb. So Coulomb found out that force between 2 charges were inversely proportional to the square of the distance between them and directly proportional to the product of those 2 charges. That is, force was directly proportional to the product of the individual charges between them and inversely proportional to the square of the distance between them. And to even out this, he introduced a proportionality constant which is K. K Q1 Q2 divided by R square. So what exactly is this K? How this is happening will be discussed shortly. So this was the thing that was found out by Coulomb. So he observed that when there were two charges separated by a distance of r between them, each charge will exert a force on the other charge. Let's say both of these charges are positive for the time being. So both of these charges will repel each other. So this will be directed in this way and this will be directed in this way. The force will be in that direction. So what Coulomb said was the force between these two charges will be proportional to their product of their masses, and we'll learn more about this Coulomb's law and how it actually operates in the coming classes. But more importantly right now, what if there are more than 2 or 3 charges present in a system? How do you calculate the force then? What if there are 100 charges? What if there are 1000 charges? How do you calculate the force between them? If there were 2 charges, we can use Coulomb's law, that is Q1 Q2 by R square. But what if there are 10 charges, 20 charges, 100 charges, 1000 charges? How are you going to do that? So for that, we have a law which you have studied in your PUC first year, that is the principle of superposition, which states that if a system has n number of charges exerting force in different directions, then the total force on that system will be the vector sum of all those individual charges. And the interesting fact is that the individual forces are unaffected due to the presence of other charges. So let's say that we place a test charge Q. Test charge, which just means that it is a unit charge placed in vacuum. So there are Q1, Q2, Q3, Q4. 4 charges are placed apart from each other, and all of these charges will exert a force on this test charge. Since all of these charges are positive, they will have a repulsive tendency towards the test charge. That is, all of them are positive. So what they will do is try to push away from each other. So this pushing sense will have a force, and this force will be experienced by test charge Q. So from here, charge Q1 will be exerting one force, Q2 will be exerting one force, Q3 will be exerting one force, Q4 will be exerting another force. So what is the force experienced by this test charge, that is plus Q? So that is what we are going to calculate using superposition principle. So basically, if there were only 2 charges, then the charge experience will be found out through Coulomb's law, that is Q1 Q2 divided by R square, and the direction will be in this direction. So what exactly is happening is that since a system contains many number of charges, don't get scared, it is the same number of charges. We have Q1 here, Q2 here and Q3 here. So we are saying that what is the charge experienced by this Q1 due to Q2 and Q3. So each of these charges, let's first assume that all of these charges are positively charged. So there is Q1, there is Q2 and there is Q3. So these are the charges Q1, Q2 and Q3. So we know that Q3 will be experiencing a force due to Q1 and Q2. How do we know that? Because all these charges are positive. Let's say all of these charges are positive in nature. So this Q1 will exert a force on Q3 and Q2 will also exert a force on Q3 because they want to repel from each other, because all of them are like charges. So they want to repel from each other. So they'll apply a force on Q3. And it doesn't matter if there are like a couple of more friends here as Q4, which is also positively charged, and many number of charges are there, it doesn't matter. So we know that they are all pushing in with the force. So they are all pushing on Q3 with a force, and we are going to calculate what exactly that force is. So just to know like how much force Q3 is experiencing, poor fellow, we have to calculate that for him. So that we know that Q1 is putting a force of F1 on Q3, and we know that Q2 is putting a force of F2 on that, and finally Q4 is putting a force of F4 on that. So the total net charge experienced by Q3 will be the sum of all these charges. So how do we calculate the vector sum of all these? If a system contains n number of charges, let's bring back the examples of Q1, Q2, Q3 again. If Q1 experiences a force of F1, F2, F3. If Q1 experiences a force of F1, F2, F3 and so on, then the total force will be the vector sum of all these forces. That is, the force experienced by Q1 will be equal to the force exerted by Q2 on Q1. So this 1, 2, 1, 3 is that if the charge is Q1, it experiences a force. So the force on Q1 will be F1. So that is denoted here as F1, or you can just call it as F total or F net. It is completely fine. And if it is surrounded by Q2, Q3 and Q4 and so on, then this Q2 will exert a force of F2 towards Q1. That is denoted by F12. That is the force experienced by Q1 due to Q2. So we can write it as F12. That is the force experienced by Q1 due to Q2. And this 1, 2 is denoting the direction. That is F1. That is Q1 is experiencing a force because of Q2. That is being denoted as 1 and 2 here. So similarly, if F12 means that Q1 is experiencing a force due to Q2, and then Q1 is experiencing a force due to Q3 and so on. Q1 is experiencing a force because of the nth number of charge in that system. And we already know that by Coulomb's law, the force experienced by charges will be equal to Q1, Q2 divided by R square. K into Q1, Q2 divided by R square. In this case, we know that it is not just two charges, but it is due to a system of charges. So we know that Q1 is the person who is experiencing all the force, and we are going to calculate it individually. So force F12 will be just Q1 and Q2, and force F13 will be Q1 and Q3, and so on. F1n will be Q1 and Qn, which means that we are only considering two charges at a time and we are going to add them all together. So what will happen? So first, we know that the expansion of K is 1 by 4 pi epsilon naught. So Q1, Q2 divided by R12 square. This 1, 2 is just the direction, that is the direction from Q1 and Q2. So Q1, Q2 divided by R12 square. And this is known as unit vector, which is R caps. This all will be discussed in the coming terms, so don't worry about the intricacies of the chapter. First, we'll get a good grasp and then we can discuss more about this, okay? So this is the unit vector, just denoting that the direction is in that way. So first we'll find out F12, that is due to Q1, Q2, and the distance between them is R12 square, plus because of the force due to 1 and 3. So Q1, Q3 divided by R13 square, and so on up to F1n. The force experienced by Q1 due to Qn divided by the distance between them, that is R1 and Rn. So all this will be added together. F net will be equal to 1 by 4 pi epsilon 0, which is common in everything. So we'll take it out, and the remaining things are Q1, Q2 divided by R1, R2 square plus Q1, Q3 divided by R13 square plus so on up to Q1, Qn divided by R1n square. So we can sum this all up. So the common thing again in this equation is that Q1 is common everywhere. So we can actually take that Q1 also outside and we can say that F is equal to Q1 divided by 4 pi epsilon naught. So that is common everywhere. And then we use this capital sigma. So this capital sigma denotes summation. I hope you all know that. And which is from I to n. I is equal to 1 here. So which is 1 to n. There are n number of charges in that system. So the summation from 1 to n. So Q1 to Qn. And Qi divided by R1I square. So we are just summing up all the forces. Basically the thing we are saying here is that if there is a system of charges present, then the total force experienced by a test charge or any single one of those charges will be equal to the vector sum of individual charges. And how can we find the vector sum? You just add up individual forces together. If a system has 3 charges and you want to find out what is the force experienced by the first charge, then the other 2 charges are named 2 and 3. Then you simply calculate using Coulomb's law and superposition principle that the force experienced by Q1 will be due to the force exerted on 1 due to 3 plus the force experienced by 1 due to 2. Like that, we'll add up all these together and we can find the total amount of force. So you can actually call it as F net or F total. I don't care what you call it as long as the formula is correct. So we already know what is the equation for force and Coulomb found out, and that is Coulomb's law, which is given by Q1 Q2 divided by R square. So we'll study what is Coulomb's law and how the directions affected and how different charges are responsible for such things will be studied in the coming classes. But for now, this is how we calculate the force on a charge due to a system of charges. I hope this is clear. And finally, there is this question of how these charges feel the force, how this force is exerted outwards. They don't have hands or like feet to exert force like us and like kick it around. So how do they experience this force? So that is through fields actually. We are surrounded by fields and each charge will have an electric field around them. So if you place a positive charge here, it will exert an electric field around it. So basically, electric field due to a charge Q can be defined as the force experienced by a unit positive charge if placed at that point. If placed at that point means that it is just the area under which this positive charge can influence its surroundings. So what exactly is that electric field, how it behaves, and how exactly Coulomb's law behaves, what is the direction, everything will be discussed in the coming class. I hope you have understood everything I have taught you here today. I'll meet you in the next class with more physics. Until that time, I'll see you again. Thank you.